Okay, so the second topic of this introduction is the interpretation of probability and Bayes' rule. All right, so this will be the only time I'm going to talk about some of the drawbacks of the classical and frequentist inference that some of you might know about, and then try to use this to motivate why we want to think like a Bayesian. So if you have heard about those terms, significant tests and confidence intervals, and they are all forms of classical and frequentist inference. However, it can be inadequate. Just to give you a small toy example here. Suppose you flip a coin and you don't know. So usually a coin, if a coin is fair, it's going to be 50% heads and 50% but tails. But suppose you don't know. You just flip it and you flip it for 3 times and you get tails all 3 times. So if you've taken a stats course before that, this is actually, if you want to know the probability of heads, this is going to be a proportion. Right? You're trying to make inference about a proportion, and it's going to rely on how many times you flip. That's the sample size, right? And then how many times you get the head. So typically, that's what we call like a p hat, the sample proportion. Let me write it over here. And yeah, so that's, you will need that for doing a classical or frequentist inference. And the sample percentage, which is p hat here, in our example, if you only flip it for 3 times and you got tails 3 times, then the p hat will be 0. Okay? But of course, you will know that, well, if it's a relatively fair coin, an estimation of 0 will be too extreme, right? You would expect it to be close to 50% or like 0.5. And in order to have valid inference, especially from the frequentist or classical point of view, you will have to flip it for a large number of times, right? And then in the long run, if it's a fair coin, if it's relatively fair, it's going to approach 0.5. Right? So the issue with frequentist or classical inference is that it does require large sample sizes. All of the methods that you have learned or you may well learn later, not in this course, in other courses, that relies on large sample size. And if you don't, then all of this estimation process will not be accurate. Okay? However, from the Bayesian point of view, you will see the way that we say it a priori. So if you know that it is a fair coin, then before you even flip the coin, we believe that the true percentage should be around 0.5, not 0, right? And then the Bayesian methods of doing this is we're trying to incorporate, before you do any kind of experiment, you're trying to incorporate your belief, in this case, through a prior distribution or prior probability. It's your prior belief. We try to incorporate that in the entire estimation process. So imagine that I start with 0.5. I believe P should be 0.5. Okay? Now I flip this coin. I get a head. So intuitively, you might increase your guess of the head probability. Right? I get 1 head. And then if I keep doing it, if I do it for the second time, I get another head. So if you are trying to use the data to update your belief about this particular coin, like the probability of the head, if you keep getting heads, it's going to go up, right? If you keep getting tails, you're going to keep going down. But it's possible it's a fair coin. If you're doing it really independent and randomly, you should just like stay put like similarly across the board of 50%. Anyway, so this is trying to say that, well, we try to incorporate the prior belief of anything. Sometimes it's your own belief, sometimes it's expert opinion that might be learned from other experiments or other studies, and you try to incorporate that. And Bayesian inference is really powerful in that case, that you will never start, like even though you're gonna have, say, suppose you still flip this coin and you get 3 times, all of them are tails, because you start a priori with 50% chance of having head then even though you're going to get 3 tails, your estimation of the probability of the head won't go to 0 because you have a starting point. Okay? And then that is helping you to correct any kind of, say, in this case, you're just unlucky maybe that you're getting 3 tails out of 3 coins. Okay? So that's the general idea. And that will be important to motivate because the classical inference usually will fail in small sample size, and then especially a p hat equals to 0, and then it will be really hard to make the inference from that point of view. And in short, Bayesian inference provides a formal method to quantifying and incorporating our prior beliefs into inference. When we say formal method, you will learn soon through Bayes' rule, and then of course more advanced models, how we can actually incorporate those prior beliefs and then combine with the data, you can come to a posteriori belief. All right, so long history, it was actually named after Thomas Bayes. It's a mathematician, also a minister in the 18th century, so that's a typical photo of him. And back then and also along the way, we do care about three aspects: modeling, and so it can help incorporate prior belief or domain expert knowledge. Theoretical, the advantage of this, it doesn't need large sample assumption, like I said earlier. Computation, this is actually like a thing that has been driving Bayesian methods to develop for the past 3 decades, I would say, because before 1990, most of the methods about Bayesian stats are just so theoretical, because computation-wise, it cannot realize the actual inference. So in the past, it's mostly, try to prove this, prove that, do some fancy models, but it's really hard to implement. However, around 1990, the Gibbs sampler, the main MCMC sampler that we're going to cover in this course, was developed. And then for the last 25 years, 30 years, because of this invention, has been seeing a lot of revolutionized advance in the computation, as well as the methods. And in the course, when we get to Gibbs sample, I'm going to assign a research paper, but accessible research paper on this topic, so you can see how things were developed back then. And we're also going to cover what's the current practice, and you will see the differences and similarities. So we're going to have a discussion about it, so you will have a flavor to see how the methods was developed, as well as how the current practice can be different from before. All right. And this will be another slide that will talk a little bit about frequentist, just as a comparison. So on the left, I write frequentist classical. So the way that frequentist or classical inference think about probability is that you have to have repeated events. And then the probability of event A, PA, will actually be the limit when you have infinite number of trials for this experiment. You're going to look at the number of times that outcome A happens over the total number of experiments that you do. Okay, so this is in repeated events how people think about probability. When we're talking about flipping a coin, that 50%, it's the same idea, right? We assume that if you're gonna, so we know that it's 50% because we already knew it, but to really think about it, it is because you flip it for a large number of times, and if you record how many times you get heads, if there's a fair coin, it's gonna be 50%. Okay? And that's the typical way people think about probability, which is great. And the only issue, or two issues I mentioned here, is what if you only have one-time event? In a lot of cases, in real world applications, or in many other cases, I would say the event just happened once. How can I think of probability? Okay? And also the small sample sizes issues that I mentioned earlier. If you flip a coin for 3 times and you get 0, what you can do? Okay? So those are the drawbacks. For the Bayesian, on the right-hand side, it is subjective degree of belief. So you can have your own, I can have mine, and then we might have different ideas of what the probability of event A could be. Okay? So we try to incorporate those. And very importantly, through Bayes rules, we are updating or making changes to the probability as new data arises. So Bayes rule in other courses, especially I would say in 241, I assume everybody took it, or even not, in Econ 209, you probably have seen this before. The form here is Bayes rule. What this is saying, so this is typically just saying that, well, generically I would say, this is a condition of probability, right? Once you know B happens, what's the probability of A happening? Okay? And typically, you probably have seen this as A and B over PP. Because we can get conditional probability from the ratio of the joint over the marginal. Okay? And what we do, we just like update or re-express the numerator a little bit because the joint can be expressed in a different way. So this is a general way of people writing Bayes' rule. But when we're making inference or thinking about hypothesis and then data, B represents data or new information. Okay? And then A typically is representing parameter of the model that you're interested in. You will see that soon more in this semester, or just generically a hypothesis. So generically we write A even B, but for the Bayes rule, when we're thinking about making inference, we're trying to figure out our belief, which is about A, which is a particular parameter or a particular hypothesis, and we're trying to update our belief by seeing more data. Okay? So for example, earlier I was talking about flipping the coin, right? We start with, say in this case, let's just say it's a fair coin, so I know PA, which is the probability of getting heads, is 0.5. Let's just say that. So we start with this, we think it's a fair coin, and then we start to collect data, which is B. And in our case, the data B is just the outcome of the coin flips, right? So whenever I get a head, I might adjust it, my P, A given B, might get higher, right? But if I get, so case one, if I first get a tail, then I might reduce my P. Okay? Intuitively, that makes sense. But then in this course, we're going to cover how much the increase or decrease will happen depends on what kind of models we use. Okay? So get the intuition for now, and then be prepared to try to see different models of how to add the data and use the data to update the belief that you have about a particular hypothesis or parameter. So Bayes' rule, like in a very simple form, it is this, and this is the core that we use. I mean, all of the stuff we're going to cover in this course and Bayesian inference in general is based on this Bayes' rule. All right, so let me just cover a couple of examples so you can see a little bit more similarities and differences between those two schools of stats, frequentist and Bayesian. So for example, if you have a study on several different but similar populations, for each of which is needed an estimate of variability, so that's like standard deviation or variance, how should one use the important prior information that the populations are similar? So what I mean, so let's say, let's just think about maybe a more concrete example. Let's see if we have, let's say on Vassar campus, let's say we want to know the variance of the number of siblings students have. Okay, let's say that's the research question. And let's assume that we want to get the variance for each of the class year. Okay, first year, sophomore, junior, and senior. So this is looking at similar population, right? If you think about number of siblings, well, if you believe that even though people are in different class years, but maybe their number of siblings from each class year will be similar, and then that means like variability wouldn't be that different. So the question here is, if we believe so, how can we make that? How can we use this information when we're trying to get a variability estimate or variance estimate of that average number of siblings? Does that make sense? Because typically what we do, I just have 4 different data sets, right? I get all of them from first year. I calculate the standard deviation or variance, right? I do that for the sophomore, I do that for junior, I do that for senior. But when you do this, you're not using any information in a sense that I actually believe that they should all be very similar to each other. Does that make sense? Yeah. So typically, that's what I think frequentist method will do. And then this is, I would say, a drawback because it's really hard to incorporate that kind of similar, like your prior belief about there should be similar. Okay? But in the Bayesian method, this kind of similarity can be incorporated into the model itself. We won't cover exactly the same example, but just have this in mind that the Bayesian methods will be able to incorporate important fine information. In this case, let's say we believe they're very similar to each other. So you might assign a similar or the same prior distribution for that variance for all of them, and then let the data together to decide what will be the ultimate variance estimate for each of the different years. All right, and also this is another thing people like to talk about when we talk about differences and similarities. So maybe one of you want to tell us a little bit, how can we correctly interpret a 95% confidence interval of anything? Let's just say the 95% confidence interval for the average number of siblings is 1.6 to 2.5. What does it mean in a frequentist perspective, if you have taken a course like that in the past? There's some caveat. We always emphasize the caveat of interpreting a confidence interval. Okay, so let's say, I was saying the average number, so let's say mu between 1.6 to 2.5. Okay. We always say that we're 95% confident that the average number of siblings is going to fall into this interval. But what does it really mean? Yes?
There's a 95% chance that the interval will capture the true number.
Yeah, so what we typically do is you will have to imagine that you can repeat this experiment for a large number of times. Okay, so every time you take a sample, you get a confidence interval, a 95% confidence interval doing all of the calculation that you learned before. And the correct way to understand this confidence interval, what we show here, is that if you do it for 100 samples, you get 100 different confidence intervals. Then 95% of the time, it's going to cover the truth. Okay, so it's not a direct probability statement about this confidence interval, because a typical misunderstanding of a confidence interval is that there is a 95% probability that theta is going to be in this, but it's not that. It's really based on that you're able to repeat this experiment for a large number of times, and then that confidence interval, so then there will be a percentage confidence level that you will be able to capture that. Okay? So it's always reversed in a sense that you have to think it like there's a caveat, and to a lot of people this is not really intuitive. But later on this course, you will see that whenever we're talking about a 95, what we say credible interval, that's, you can think of as equivalent, but really it's a probability statement. Say, for example, if I come up with a credible interval of mu equals to 1.6 to 2.5, what we're saying really is that we have, and if it's 95%, let's say, then what we're saying is that there is a 95% probability that mu is going to be in that interval. Okay? The key difference here, which I will cover, I guess, in the next slides as well, is that in the Bayesian inference framework, we assume that the parameter is random. In this case, we're assuming that mu is random. We don't know about it. But the data that we get is fixed. Okay? So that means I put a random distribution for my mu, for example, and then I collect data. And use the updated data, I come up with a 95% credible interval, but it's still a direct statement about the unknown parameter mu. Because it's working on mu directly, then when we're talking about a 95% credible interval, it's a probability statement. Whereas in the frequentist, which some of you are exposed before, that was the parameter is fixed, but the data is random. In a sense that, well, I just want to know about this mu. I don't know what it is, but it's assumed to be fixed. Every time I take a sample, it's random. And I have to imagine that I can take a large number of samples. So that's why, because the parameter is fixed, whenever they're talking about confidence interval, it's not about a probability statement about the mu itself or theta. It's really about that if you can repeat this experiment that many times, and then every time, or like in total, 95% of the time, the truth will be covered. So that's the main difference, and then that actually leads to the different interpretation of a 95% confidence interval. and a 95% credible interval, which we're going to see a lot throughout this course. All right, so let's just look at a toy example. So we're not just talking about big ideas and differences and similarities. So the general procedure for Bayesian inference, notice that the goal is to make inference for an unknown probability, unknown quantity. And the quantity, maybe it's a mean, maybe it's a proportion, maybe it's a particular parameter in a model. And then this procedure is, we first of all going to have a prior probability before seeing any data. Okay? And let's say we're doing hypothesis testing in this case. So we come up with a probability of the hypothesis. You can come up with anything. Okay, it's not important now, but just keep in mind that you do this, you have a prior distribution or prior probability in this case before seeing any data. And then you're going to collect data. And you're going to go to what we call posterior probability, which is conditional. Okay? And the condition is on the collected data or the new information. Okay? So this was like what we had PA previously, remember? Right? And let's just say all of the data are B. And then we come from that to the condition of A given B. Okay? But in the general framework, it's about the data and the hypothesis. Make sense? Yeah, so the key is, again, we are trying to make inference about an unknown quantity. We're going to start with a prior probability, then collect data, and then update or sharpen our belief about that hypothesis, given the data. Another feature of Bayesian inference, which you will see in the homework question, is that we do a lot of sequential updating as well. Like say, what I was talking about flipping the coin is that, well, I believe it's 50% of heads, right? And then I flip one. If it's a tail, I might decrease my belief a little bit. And whenever it starts to decrease, it's updating to your posterior probability because I add data to it. But the thing is, you can keep adding data, right? When you just get, like, say, for example, if you get three tails or like 10 tails in a row, you might become a little bit suspicious, right? But you can still keep getting it. Maybe you were just unlucky that you're getting 10 tails in the first time. Okay? So the hypothesis, your probability for the hypothesis, the posterior can be kept updating along the way. So that's another good feature about Bayesian inference is that especially a lot of, like, I would say online recommendation system, that kind of stuff. And because you are keep getting more data from the users or whatever, right? And we're really hoping to use any new information along the way that can help you sharpen your hypothesis or like the posterior probability for the hypothesis along the way. So these are important features as well. So lastly, p-value is another thing that tricky to interpret from the frequentist point of view. And typically we write it that it's going to be the probability of data given the hypothesis. Remember, for particular or like a standard interpretation of a p-value, let's say 0.04, then what it is like under the hypothesis, I mean, the null is true, then we have a 0.4 probability to see something as extreme as our data, right? So that again is assuming that the data is random, and then the hypothesis is fixed. So that's again non-intuitive interpretation, or I should say, it's the correct interpretation of p-value. A lot of time it's not intuitive. Whereas for the Bayesian approach, we just focus on the hypothesis, and we're keeping adding the data. So the data goes into the conditional. So we won't, I mean, people rarely talk about like there are people define Bayesian p-values, but we won't talk about them in this class. But again, I just want to show you that p-value from the frequentist point of view is counterintuitive, but we always focus the correct interpretation of it. But then the Bayesian point of view is we focus on the hypothesis, and then we're trying to use data to sharpen our hypothesis. Okay? And then it's really a conditional probability. It's a probability statement about the hypothesis itself. Great, I think we're right on time. So on Thursday when we come back, I'm gonna cover this point example. We're gonna do a little bit exercise. Some of you might have seen this similar example before, but this is just using Bayesian to answer a simple question, and then from there we're gonna do more topics.